the last lecture in this conference. So it is Jesse Pontigo Herrera who will speak about a bound for the length of iterated integrals in the first non-zero Melnikov function.
Okay. And can you hear me? Okay. Well, first of all, I would like to thank the organizers. It has been a very nice event. And also, this is my first time here in Rio, and I'm very happy to be here. And although we have been having a raining week, it has been very nice, I think. And also, thank you very much for the opportunity to give this talk. So I will talk about a bound for the length of iterated integrals in the first non-zero Melnikov function. And this is a work joined with Papa Mardesic, Dmitry Novikov, and Laura Ortiz. And to start to talk about it, I would like to begin with a motivation. What this could be interesting to find a bound for the iterated integrals for the length of iterated integrals in the first non-zero Melnikov function. So we start with giving the context. So the context is, of course, it has to do with infinitesimal Hilbert 16th problem. So, but we can start with a polynomial. Actually, we could begin directly with some complex polynomial, but in the classical situation, one begins with real polynomial. If one begins with the real polynomial, one considers the complexification, but it's the same if we start directly with complex polynomial. We take some element in the first homotopy group. I call it gamma of T0, where T0 is a regular value. And we can think of it as a vanishing cycle. So I will draw the real picture because it is easier. So we can think of it as a continuous family of periodic orbits. One of them is gamma T0. And we want to know what happened in a neighborhood of this cycle when one performs a deformation. So in order to study this, one considers this a transversal to this family, which is actually parameterized by the values of the Hamiltonian. Here we are in the Hamiltonian foliation defined by this polynomial f. And we do this deformation of this type, where eta is a polynomial one form. And what happens is that generically, the periodic orbits here, they break out. So we can end up with something like this. And so when one considers a value here, t, we actually consider the first return map of this deformation. And we call it P of t, eta. Okay, and actually what we consider is not exactly the first return map, but the displacement map. This depends on t and on epsilon. And since everything here is analytic, well, we can develop it with powers of epsilon in this way. And this is where these Melnikov functions appear, as it was mentioned also in the talk of Hussein. These are these Melnikov functions. Which are also called in the literature as Poincaré-Pontryagin functions. Okay. But one can also look at this picture directly in the complex context because, well, I want to mention it because I am considering this f directly as a complex polynomial. So if we want to look the complex situation directly, what is happening locally is that you have a family of cylinders. And here you consider just an element of this, the local homology. And when you do this perturbation, the cylinders can wrap around, like making a roll here. Not a good picture, but something like that. Okay, and what is interesting here is to look how many of these periodic orbits persist after the deformations, and they are associated with the zeros of the displacement map. So in the context of the infinitesimal Hilbert 60th problems, we want to find the bound of the zeros of this function. And actually, well, I will write it. And it has been also mentioned by Hussein. Zeros of this displacement function in terms of the value t, for epsilon small enough, they are bounded. Actually, in this situation, one is supposing that, assuming that this displacement map is not identically zero, it means that there exists at least one of these Melnikov functions which is not identically zero as well. So it means we can develop it starting from one order, let's say one order mu. We have m mu of t in higher order terms. We are assuming that this is not identically zero. And then zeros of this displacement map, they are bounded back by zeros of this first non-zero Melnikov function. Okay, this is 0. Yes, and this is why you are interested in studying this function. And it was one of the first bounds for zeros of these functions is what Ilyashenko talked us about in his conference. They found a first bound for this number of zeros. This is what he, with Gal Bignamini, Dmitry Novikov, Sergei Yakovenko, it was 2010. They provide a bound, an explicit bound for this number of zeros, and therefore for the limit cycles appear here, which is this double exponential. 2 to the power 2 to some polynomial, where n the degree of the one form eta, making the deformation, and the degree of the Hamiltonian f is n plus 1. Yes?
It's not for mu equal 1, the result?
Yes, exactly. Okay, of course. This is if M1 is not identical. That's important. Thank you. Yes. Okay. I forgot to mention something also important. So if you are interested in studying this function, one can start studying the first order functions. And this has been also mentioned in Hussein's conference, which is the Poincaré-Pontryagin theorem. that the first order Melnikov function is actually something very simple, which is an Abelian integral. And in this situation, for this first explicit bound, is assuming that this is not identically zero. So the problem of bounding the number of limit cycles appearing in the deformation is the problem of finding a bound for zeros of Abelian integrals, yeah, which is given explicitly in this double exponential. And now, what has to do with our result I want to talk about is what's happening in higher order Melnikov functions. So let's see what's happening there. Okay. Yeah, in that case, what we know, well, it is known that using this Francois algorithm, one can compute the next Melnikov function in case this is identically zero. So we know that this is this Abelian integral. And if this is identically zero, then there exist some functions locally analytic, G1 and R1. And here they are defined in a neighborhood of the initial regular value, such that our form eta is expressed in this way. This is analytically, locally, relatively exact. And with this expression, Francois' algorithm tells us that M2 can be computed just as the integral of this function G1 appearing here times the form eta. Yes? And again, if this is identically zero, one can reproduce this statement. Then looking at this one form as an analytic one form, there exists some analytic, local analytic G2 and R2, okay, such that now G1 eta is relatively exact. And so on. And actually what happens in generic situation is that these functions, they are not only locally analytic, but they are polynomials. This was the kind of expression that Pavao showed us in the Darboux case. I think also Daniel talked about this kind of expressions in the global situation. But here it is only local, and this, because they are not polynomial, they will produce some problems. They will produce what we call these iterated integrals. And to talk about them, I will use another expression for this Melnikov function. So this will be a remark. From this expression, if we consider the exterior derivative, then we have that d of eta is d of G1 with df. And then we can think of dg1 as this, the form defined by d eta over df, which is what is called the Gelfand derivative. Gelfand-Leray. Which is well defined in neighborhood of regular values. This is is actually a rational one form. I will use actually this notation, gamma prime. And also from here, one can reproduce this formula. D of G1 eta will be now the G2 with df. And then we can think of dG2 as the Gelfand-Leray derivative of G1 eta, where df, which is eta prime, eta prime. Okay? In using this Gelfand-Leray derivative, we can rewrite these Melnikov functions for instance M2 as this iterated integral. The integral of, this was in the beginning G1 eta along gamma of t. This can be written as eta prime eta along gamma of t. Just to recall what is an iterated integral, I will write it here. The definition of iterated integral, this was also given by Hussein in his conference, and I will just do briefly a recall. So essentially, you have some surface, S, and you have here a path, say L, and you have some meromorphic one forms, let's say omega 1, omega 2, and the integral, this is kind of symbolic function, but what that means is to integrate along this path, but to take some kind of sub-path here, let's say L1, which is given by some restriction of this path to some sub-interval, D0 to T1, and then you define with the function omega 1 an analytic function along this neighborhood of this path by integration. And then this function you multiply by omega 2, and then you integrate along L. Yes, and you can repeat this for any number of meromorphic forms here. This is essentially how we are defining this Melnikov function with iterated integrals. And okay, I would like to mention some properties of iterated integrals that I think they will be important to know. For example, let's take some properties. For instance, if you have something like this, consider P a rational function. This is one form, and take another form, omega, along some path L. This can be expressed as P multiplying omega minus this along L. P to evaluate it to the initial point of the path, let's say L of 0, multiplied by the integral along the path. So actually, P could be just a meromorphic function or locally analytic. But in the case when P is actually rational function, it means that initially you have something written as an iterated integral of two forms, let's say of length 2. But it can be reduced to something that is of length 1. If P is rational, then it means This is also rational one form, and it means that it's what we call Abelian integral. So when we talk about the length of the iterated integral, it means the minimal expression as iterated integral. It can be reduced. Yes? Another property is this. If you have, for example, this iterated integral, and you want to integrate along the concatenation of two cycles, then what you have is the integral along one of them plus the integral along the second cycle, but you add some extra terms which are given this way. They are called shuffle terms. And in particular, this means that iterated integrals, they are no longer abelian. No, they don't open up the concatenation of cycles. Yes, you have this extra terminus which they provide a kind of multi-evaluation of these functions. Okay. Okay, I will write here. Before coming back to Melnikov function, I want to point out another remark about iterated integrals. And these objects have been studied by Chen. I think he did a lot of publications about these objects. And what he developed is a kind of the RAM homotopic theorem, or homotopic de RAM theorem. In this way, let's consider the same surface S and consider the lower central series. Let's say let the pi 1 the first homotopic group of F. We call it L1. Then you have lower central series. Which is a filtration of some commutators inside the surface S. I will call this L2. This will be L3. I will use this notation later. And in general, Li plus 1 is just commutators with pi 1. The left-hand side remains as pi 1. And in that case, what actually was proved by Chen is that if you take only commutators of length I, and consider, well, tensor with complex in order to have a vector space, the dual of this space is generated by iterated integrals of length exactly I. So in the philosophy of the RAM theorem, where in the classical situation you have an element of homology and you have its dual, which is a one form. Here you have any element in homotopy group and you associate a dual, and the dual is given by this object, iterated integrals. And actually, since the bigger the length, and it can detect also a bigger commutator. It's a kind of, the length is a kind of measure of the complexity of these functions. Okay. Well, I will end up the remark here. Now, coming back to Melnikov functions. Okay. So, using this Gelfand-Leray derivation, so we saw that M2 is an iterated integral of length at most 2. No, it can be reduced, maybe, by this was the first property of iterated integrals. But for example, also from here, we have if now M1 and M2, they are identically 0, we have that M3 can be expressed by eta prime multiplied by eta. And actually, the sign is alternating. So it is, this expression means that M3 is iterated integral of length at most 3. And in general, if from 1 to mu minus 1, they are identically 0, we have that the first non-zero Melnikov function can be expressed in this way. It's minus 1 to the power mu, the integral along gamma of t, by this Gelfand-Leray derivative. Gamma t in L where?
This formula is valid only for certain gammas, certain cycles.
Ah, homology.
Yeah. It's
Okay.
not valid for any cycle. For an arbitrary cycle, it is more complicated.
Okay. Yeah. Actually, from the beginning, I was okay. Maybe it's not so general. So I consider it in homology. Is that that's what you mean?
No, well, it is valid only when gamma is inside this Li notation that you have written. Gamma is
Li.
commutator of the commutator of the commutator.
Ah, okay.
It
It have a product or something like that.
Yeah.
It's not
Yeah, there are
longer valid. Okay.
Integrals of less lengths also. I have written this one with the Bomer. I will show you.
Okay. Thank you for the observation. Okay. Well, but from here then, here is ortho prime. When we develop this derivative, the biggest iterated integral that can appear is of length at most mu, at most the order. Okay. And okay, so coming back to Hilbert, infinitesimal Hilbert 60th problem, it has been proved also there is an explicit bound in the higher order situation. It was provided by, in 2011, by Benditkis. And Novikov. And they show that the number of zeros of a mu, where mu can be general from 1 to any natural number, then they gave a bound that it is also doublet exponential to m, where m is the degree of eta. To some explicit expression, they call it O of 1, of order 1, and plus 1 is the degree of the Hamiltonian, and this is to the power of something that depends on the order. But what they actually need is a bound for the length of iterated integrals appearing in this first non-zero Melnikov function. They take mu since from Francois' algorithm, we know that, it is known that it cannot have iterated integrals of length bigger than mu, so they use mu. But actually, if one can provide a better bound for the length, this expression can be better. And also another problem about this bound given by this order is that it depends explicitly on the deformation. And it's not an optimal bound. And what we show is that actually one can provide another bound that does not depend on the deformation, but depends only on the topology of the regular fiber of the Hamiltonian and on the orbit under monodromy of the cycle gamma. I will write that down here. But before to write the result, I will see an example. In the generic situation, which was studied by Lashenko, it is known that mu, whatever the order is always an Abelian integral. And actually it follows from this tangential center problem where in this generic situation, this vanishing of this integral implies that there exists this G1 and R1 that we used in the Francois algorithm. They are polynomial. And eta can be expressed, can be given in this global expression. And from there, well, for example, M2 is again an integral of a rational one form. Therefore, it is an Abelian integral, and one can repeat the same argument. It's a way to see that it's always an Abelian integral. So it means that at the end, just having these generic situations of the polynomial f implies that the length of the iterated integrals appearing here is not increasing. So it's somehow something attached to the topology of the fibration. Okay. And the theorem is that, well, if this is with Mardesic, Novikov, and Ortiz, that there exists a constant, K, such that the length of this first non-zero Melnikov function is bounded by this constant, where K depends only on the topology of the regular fiber of the Hamiltonian. And also on the monodromy, in the orbit on the monodromy. Of the initial cycle gamma of t. And I'm not sure if that was necessary, but I think that was.
Because if you go in the sequence that you wrote in this Chen's, so if you go further deep in the sequence, then there will be more and more Melnikov functions there. I don't know.
I'm not sure about it.
Wait, what does it mean? Depends on the topology of the how it depends.
Yeah, in terms of this first.
You don't know. I mean, if you don't know how it depends, you say nothing.
Yeah, this is because we are only using the first homotopy group in that terms. You only need the first homotopy group, and you're working on it. And I think that's we only need about the topology of F.
Maybe you can say what is K.
Ah, what is K?
This will answer the question.
Okay. I will define it. Yeah, this will answer the question. Okay. Yeah, I will define it now, but before, okay, I will do it now, maybe. Let me have a look at it. Yeah, I have to talk about a little about the monodromy in order to define this K. So we need monodromy. I think it was, this is something that was also mentioned in many conferences during this week, that, well, this is essentially considering this minor fibration defined by the polynomial. This is a local trivial topological fibration. And this allows us to move from one surface to another. So we remove these points, which are they are not infinitely many. So we remove them. This is those are atypical values. And any other value, we have the same topology. And we go around these atypical values, and we saw what's happening with cycles in the first homotopy group. So we can start with this cycle, and at the end of this, going around this value, we can end up with something that also goes around this, grabs another cycle in the surface. And the orbit under monodromy, this is a group generated by the images of all the cycles that you can get by monodromy. Take the monodromy along any element in the first homotopy group of this base of this cycle gamma. And this is a normal, actually we take the smallest normal subgroup generated by the elements in the obtained by monodromy. This normal subgroup of the first homotopy group of the surface, which is the preimage of the regular value of f. Actually, we are with a fixed value d0. Okay. Now, actually, I will use again this Lagor central series to define this constant k. So we have pi 1, which is L1. And we define k as the supremum of j greater or equal than 1, such that O of T0 intersection Lj is not contained inside this commutator. Commutator of the orbit with pi 1. Equivalently, this is the minimum of j plus 1. We call it I, such that the orbit intersection Li plus 1 is contained in the orbit. In the orbit commutator with pi 1. Okay. Case kind of filtration of which commutators in the orbit do not belong to this space. I hope I have a little time to explain why this is important. But okay, this is the definition. We call it orbit depth. How deep the orbit is. Okay, now I want to give some examples where this theorem is applied. Actually, the generic case, one of them. So in generic, what was proved by Ilyashenko is actually that he uses in also to show that M mu is always an abelian integral, which provides analytic continuation, is that the orbit generates everything. Yeah, and from there, in the definition of the orbit depth, what we have is that, for example, L2, which is pi 1 commutator with pi 1, is the same as O commutator with pi 1. So it means that the orbit depth is k equal 1, which is it means that the length is bounded by 1, so we always have abelian integrals. There are some non-generic. For example, you have product of lines in general position. You have centers. In this case was studied by Marco Uribe. And also there's a generalization of it where you allow some degree greater than 1. This was by myself. And where you essentially have the same behavior as this configuration of lines in general position. In both cases, you have that the length of the first non-zero Melnikov function is at most 2. And it is proved independently in one of those cases without using this orbit depth. And here, this is non-generic because we have, well, in the generic situation, you have to have morph critical points, transversality at infinity, and also all the critical values have to be different each other. But in this situation, this level 0, you have this product of line, product of curve. So all these critical points, they are sharing the critical value, the 0 critical value. So we have f, this product of polynomials. But this means this means that the orbit is no longer generating the whole first homotopy group. And what we are not getting, this complement of the orbit, this provides some extra elements in this tangential center problem. It means eta is no longer something algebraically relatively exact, but you have to add here in both cases some forms which are given in this way, some logarithm 1 forms. And those extra elements, they are responsible of the increasing in the length of the first non-zero Melnikov function. But we can also verify that this is actually of length at most 2 by computing the orbit depth. I will write it.
For example, in the Ashoka result, the cycle must be vanishing cycle. Otherwise,
Okay.
if you take average cycles,
Maybe it's not. Yeah, if you take commutator already, you cannot generate everything. At least generate case, but
for example,
okay.
the cycle at infinity, they are just invariant on the
Yeah, you cannot generate anything. Yeah, but also this constant, it depends on your cycle, no? It depends on the orbit. So it means if you're not getting something, it will be, you will see it here. No, if you're already with commutator, you are not longer generating everything. You will get extra terms, and for sure you will get here an increasing of the length too, as well. So, but in the generic, yeah, you're right. I think it is important that it's in homology. Yeah, let's say here I'm using homology. If no, you cannot generate everything. So in both cases here, one can prove that actually L2 is contained in the orbit under monodromy, and this implies that L3, which is defined as L2 commutator with pi 1, this is inside orbit with pi 1, and therefore this is already inside this with definition of orbit depth. In this case, it's equal to 2. Yeah. And there is another non-generic situation. And when we are no longer in this kind of configuration, when in this configuration we don't get any problem at infinity, but let's take now two pair of parallel lines, this square case, where you have this center critical point. And in this case, it's very symmetric. And this symmetry will produce that the orbit under monodromy of this cycle will be also smaller. And in this case, it happens that k goes to infinite. Yes. And that was very surprising to us because when we provide this example, we were looking for the next number. We were looking for something to get k equal to 3, and it jumped to infinite. And actually, if you do a slight deformation of this, let's say we lose a pair of parallel lines, you produce here another center, then in this case, k go to 2. Yeah. So, okay, it's a kind of a strange phenomenon. It's not, it goes from infinite to 2. Okay. Now maybe I will do a little sketch of the proof. Yeah, here we provide some deformation with length 2 and length 3, but we were not able to produce deformation with length greater than 3. There is a kind of strange phenomenon there. Okay, I'll do some steps about the proof. One of them is that, well, the first step here is to observe that mu, the first non-zero Melnikov function, it is actually defined an element of the dual of this quotient it belongs to its dual. It is defined by taking any cycle here, and you assign the corresponding Melnikov function at this value, T0. And this is due because this is the principal part of a power series. And by properties of power series, actually, one can prove that they vanish in this kind of commutators, and they are also linear on the orbit by monodromy. You have to use also some analytic continuation argument. But so we have here a linear function defined by the third non-zero Melnikov function. So in order to describe this element, we have to describe this space. So second step is to try to describe this space. I will call it CHO. It's kind of homology restricted to the orbit. So in order to provide a better description for this space, we have to consider a filtration of the commutators that you can find in the orbit, not lying in this commutator. So we define some IOI, like O intersection Li, divided by this commutator, intersection Li. And on the proof, this is included in this OI plus 1 is included in OI. So what we have actually is that this space can be expressed as the direct sum from I plus I1 to infinite of this quotient, OI over OI plus 1. And now from the definition of the orbit depth, we have, if we already have calculated this number, it means you don't need to take until infinite, because in that case, OK plus 1 is trivial. And actually, OJ, for any j greater or equal than k plus 1, they are also trivial. And then you can express this space only from commutators to 1 until the orbit depth. So there are only, at most, commutators of length k involved in this situation. Yeah. So the third step of the proof, I'm not sure I will have enough time, but if the idea is to reproduce this Chen theory about the homotopy, the Ram theorem. This is a Chen's construction. That will provide a basis of iterated integrals generating this space. The dual of this space. It's okay. But the Chen's construction is a little bit, we need more time to describe it, but the idea is to define a linear equation where you have some iterated integrals involved. Let's say you have to define some the Chen connection inside some Lie algebra. This, you will take the polynomial basis of cohomology and you search for an horizontal section, which is, well, we are working in this universal covering of your surface. This trivial fibration with this G will be some Lie group. So the horizontal section is like solving a linear differential equation, and the solution will provide some map that's called the Chen map, which is given by these iterated integrals. Here you have some of iterated integrals along some path connecting this point to another base point in this universal covering. And these iterated integrals appear by Picard iterations. This is a way to solve differential equations. But you have here any length iterated integral. Then you have to pass to the homotopy group by restricting to the inverse of this universal covering to some base point. Then you can descend this operation to homotopy. And then you have to restrict to only polynomials. They're actually non-commuting polynomials. These extra variables that are used to define a Lie algebra, which have this Lie group. You restrict to some polynomial of degree at most k. And the idea is that these iterated integrals appearing here, defined by this polynomial basis of the cohomology of the surface, they will be used to define a basis, a good basis for this space in order to express the first non-zero Melnikov function with iterated integrals. But actually, in this expression, they are not good enough. You need to consider the logarithm of this expression. Then you will no longer have these integrals, but some you will mix them up. But these mixed iterated integrals, they will have the good properties. This is due to Baker-Campbell-Hausdorff formula. But because at the end, some sorry? Erased one. Ah, yeah. I have composed it with logarithms. Thank you. Well, to finish, only the idea is to show that this space is isomorphic to the space generated by this logarithm, this Chen map, until k, order k. This is of the orbit divided by the extent of this space of this commutator. So when I was talking about the Baker-Campbell-Hausdorff formula, this is in order to see that with this operation, we actually have this isomorphism, because when you get extra terms, they will go to the quotient. And roughly, this is the idea of the proof. And just to end, I want to point out some questions. I think Pavel mentioned one of them. The question we have around this problem. One is if this bound we have found is optimal or not, which it was related with Gavrilov's question. Is the orbit depth optimal? Which is the problem of realization. If we can realize, for instance, if in the case k equal infinite, if you can always provide a deformation having iterated integrals of any length, I'm not sure about it. Another question is, can be 1, 2, and infinite only possibilities? Or you can provide another example having k equal to 3, 4, etc. Because for the moment, we don't know any other example between these two constants. And the other is if there are some relations with singularities at infinity. Because also in the case of this example, it seems important to have this kind of behavior at infinity. So we think that maybe by studying the singularities, you can conclude that k must be infinite. But my time is over. Thank you.
So before letting the questions, I just wanted to make one comment. I think something that you didn't have time to mention. It was the paper of Lyubomir and Ilyev, where they study somehow the case where they characterize when iterated integrals will be somehow Abelian integrals, which somehow strongly inspired what we did.
Yes, yes.
Questions?
I have maybe an heuristic confusion. It's because, well, you always use homotopic class, not? And it's justified because you are used this Chen homotopy.
Yes.
But I don't know, maybe in these cases that you give an example, the Ilyashenko, maybe this product of lines when you consider the tangential problem and so on. In these cases, it is possible to use only homological classes. So for me, it's like, okay, this technique part, okay, you use homotopy class, but this is my heuristic confusion because it's not enough to consider only homological classes and something like that, like at the vector space generated by the homological classes.
Yeah. Actually, what Marco did, and also in the other example of divided, and it has been proved only using homology that the length is at most 2. And in this kind of statements, we have to use homotopy in order to get some general cases. But in some restricted situations, I think you can restrict yourself to homology. But the problem will be if you are working with something maybe with a lot of symmetries, then you will get some extra terms that you will see in the cohomology, the RAM of the surface. And it's not easy to see if these extra terms, theoretically, you will get maybe some iterated integrals of very big lengths. But to reduce the length is not a trivial answer. So maybe you will have complications if you don't go to homotopy in that sense.
Okay, thank you.
maybe I would just say somehow that I think homotopy is kind of natural in this problem because we work with multi-valued functions and it is not commuting. Essentially, somehow commutators are something what is key in the problem, and somehow then homology is not. But of course, I mean, you can somehow go around using homology, but you have to take care of what you are doing, and so it's. But it's probably more. I think it's more complicated if you. Sorry.
There's a notion of local system, and there are homology classes of local systems. Yeah.
Other questions? Sure.
Well, according to my experience with lines, maybe for the second problem, 3 lines passing through a point, and maybe if the fourth line intersecting them.
In which situation? In that one? Or?
No, for the maybe intersecting our lens 3. What I'm saying.
Triangle.
3 lines passing through a point, and the fourth line, which does not pass. So this is a kind of degeneration of 4 plus 4 lines.
Yeah.
In general position, we will have the Picard-Lefschetz theory, but when 3 of them pass through one point, the depths might increase. Okay.
Maybe. Yeah.
Other questions? So do you want Hussein to that we come back to the question that you asked? Or?
No, I was just complaining about the theorem, the delta is branching cycle was missing.
Yes. Yeah.
Just in the theorem.
Okay, I agree. And your complaint, Ljubomir?
No, I don't complain. I think it's a very, very, very good result. Expected in a sense, but the notion of depth, in fact, I suppose that it should exist somewhere in other branch of mathematics. It is very natural, but now it appears in dynamical systems. So this notion is very important. So it's a very good result.
Thank you.
Other questions? Other complaints? So if there are no questions, let's thank Jesse.